Last time, we handed our model a single bucket. One RC pair. And it did something almost magical. The flat response of the resistor bent onto the real curve and caught the knee. But watch the tail. Minutes later, the real cell is still drifting. And our one-bucket model has already flattened out. We know the name of that drift now. Diffusion, the Warburg tail. But the element that captures it won't run inside a controller. So engineers do something pragmatic and a little bit sneaky. If one bucket isn't enough, use more. We're not going to reach for the exact physics yet. We're going to approximate that long tail with a ladder of buckets. Each one a resistor and a capacitor. Each tuned to catch a different speed of relaxation. A fast bucket for the quick knee. A slow bucket for the long tail. This is the NRC Thevenin model. And quietly, it runs in more battery systems than any model on Earth. It sounds like a hack, and honestly, it is one. But it's a hack with 100 years of theory behind it. Whose idea was it? The frame comes from Leon Charles Thevenin in 1883. Any linear source, however complex inside, looks like one source behind one impedance. Our job is to build that impedance out of parts we can compute. And the latter trick is older still. A Foster network, a way to fake a continuous impedance with a handful of parts. We're not discovering physics here. We're engineering an approximation and being honest that that's what it is. But there are two ways to stack these buckets. Nest them inside each other, and you get a Cauer ladder. Line them up in series, and you get a Foster network. We use Foster, and there's a reason. In a Foster ladder, each bucket can stand for one physical process. So the model isn't just curve fitting, it's a story you can read. Here's our model now. The OCV source, the instant resistor R0, and then two buckets in series. The fast one, R1 with C1, has a short time constant, a couple of seconds. That's the charge transfer knee. The slow one, R2 with C2, has a long time constant, tens of seconds. That's our stand-in for diffusion. 5 numbers to find. V equals OCV, minus I times R0, minus V1, minus V2. And these two buckets aren't arbitrary. The fast one, a couple of seconds, is charge transfer. Ions crossing the interface, piling up in the double layer. The slow one, tens of seconds, stands in for diffusion. Lithium wading through the solid, the slow soak we met last time. 2 buckets, 2 real processes at 2 different speeds. Now the money's shot. We fit those 5 numbers to the same measured pulse. And look what happens that one bucket never could. The fast bucket snaps onto the knee. The slow bucket bends down the long tail. The dashed model line and the real curve are now almost impossible to tell apart. The gap we've chased since Lecture 2 is finally gone. So how does the computer find those 5 numbers? It hunts for the 2-time constants. Watch them separate. One slides down to about 2 seconds, the fast process. The other settles near 20, the slow one. Once the timescales are set, the resistances fall out by least squares. A search in time, and then a solve. And because we built it, we can take it apart. Peel the voltage, drop into its pieces. This instant step is R0. This fast decaying band is the first bucket, V1. This slow, lingering band is the second bucket, V2. Each element is doing exactly one job. That's the beauty of a circuit model. Every piece has a meaning you can point to. And this isn't a toy. A 2RC model like this runs inside real battery management systems. In electric cars, in grid storage, in the phone in your pocket. When your screen shows a battery percentage, something like this is often underneath. But nothing is free. Every bucket you add is another differential equation. One the computer must solve every time step forever inside the pack. One bucket, one state, two buckets, two states. Watch the compute cost climb. This is the trade at the heart of all modeling. Fidelity is bought with speed. Remember where this runs. A battery management chip is small and cheap and busy. It solves this model for every cell in the pack, many times a second. 100 cells, 1,000 times a second. The states add up fast. So why did the industry land on 2? Not 5, not 50. Add a third bucket and watch. The fit barely improves, but the cost keeps climbing. We've hit the point where the leftover error isn't the model being wrong. It's the measurement noise in the data. Fitting harder past that just fits the noise. 2 RC pairs is the honest sweet spot. Fast enough for real time, accurate enough that the cell can't tell. But wait, how did we know to use exactly 2 buckets? And how did we know where to put their time constants? That turns out to be its own science. Ask for too many buckets, and the fit becomes ambiguous. 2 different sets of numbers can match the very same curve. We'll face that head-on soon. For now, hold the question. So, are we done? We have a model that tracks a real cell almost perfectly. Let me try one thing. We fitted these 5 numbers at 50% charge at room temperature. Let me keep the exact same numbers and run the cell cold. Watch. The model peels away from the real curve, badly. The error jumps from a fraction of a millivolt to tens of millivolts. That's not drift, that's the model failing. And now, low state of charge. It diverges again. And it makes sense. Cold slows every reaction, the resistances climb. So the numbers we fitted at room temperature are simply wrong now. Our beautiful model was only ever true at the one spot we measured it. Let's step back for a moment. We began with a resistor that could only jump, never bend. We gave it 1 bucket, it caught the knee. We gave it a second, it caught the tail. And now our little circuit tracks a real cell almost perfectly. 5 numbers, 2 buckets, 1 honest model. As long as nothing changes. R0, R1, C1, they aren't constants at all. They're functions of temperature and of state of charge. So next, we stop pretending our parameters are numbers. And we turn them into maps.